Okay, so we have seen that for the support vector machine, gamma ref is actually just the margin of our decision boundary. So how can we actually write gamma ref in terms of things that we know, in terms of theta and theta naught? Well, to answer this question, let's first observe that we can actually scale theta by any constant without changing our decision boundary. This is because theta describes the orientation of this normal vector. So we can scale theta by any constant. It will only change the magnitude of this vector, but will not change the orientation of this vector. So in turn, our decision boundary would not change. So here we see that we actually have some room to play with in setting what our theta actually is. So now let's look at gamma ref. Gamma ref is the margin, which is the distance between this point that's closest to the decision boundary and the decision boundary. Let's call this point I equal to m. So in that case, gamma ref would be just ym times theta dot xm plus theta naught over the magnitude of theta, just using the definition here. So we just said that we can scale theta by any constant without changing our decision boundary. So let's follow convention and just scale theta such that we set this value, ym theta dot xm plus theta naught, equal to 1 exactly. And in that case, we can now write gamma ref as simply 1 over norm of theta. And we have successfully written gamma ref as something that we already know, which is theta. So now if you plug in gamma ref into our function, our objective function, and do some simple simplifying, we get that the objective function for the SVM is equal to 1 over n, sum of I equals to 1 to n, hinge loss of yi theta dot xi plus theta naught plus alpha, which is our hyperparameter, and plug in alpha ref into here, plug in 1 over norm of theta into here. Our regularization term is just norm of theta squared. So again, kind of tying back to the previous video, this part here is the loss term. Which is a function of theta, theta naught, x data, which is the x data points in the training set, y data, which is the labels of the training set. And here our regularization term is this here. And we see that indeed it is exactly just a function of theta alone. And again, balancing these two terms is the hyperparameter alpha. And now we'll see how different values of alpha affects the performance of our model.